Hi, welcome back to recitation. In lecture, you learned about some new tools for computing certain limits. In particular, you learned about L'Hopital's rule. So now you have the ability to compute easily some limits that before might have been difficult to do. So I have here 4 examples of limits, some of which, or maybe all of which, or maybe none of which, or, well, definitely some of which, will be, you can use L'Hopital's rule on. So here they are. Why don't you pause the video, take a few minutes to work them out, come back, and we can work them out together. Welcome back. So we have these 4 limits here, and let's start solving them, shall we? So I'll just go from the first one, and then I'll go through them in order. So limit A is the limit as x goes to 1 of x to the a minus 1 over x to the b minus 1. If we want to use L'Hopital's rule, we have to first check that this is a limit of an appropriate kind of expression. So that's, in particular, a limit that is a 0 over 0 or infinity over infinity form, so an indeterminate quotient. And as x goes to 1, we see that x to the a goes to 1, so x to the a minus 1 goes to 0, and similarly x to the b goes to 1, so x to the b minus 1 goes to 0. So indeed, this is a 0 over 0 indeterminate form, so we can apply L'Hopital's rule. So we apply L'Hopital's rule, and it says that the limit as x goes to 1 of x to the a minus 1 over x to the b minus 1. OK, so what do we do? What L'Hopital's rule says is we can take the derivative of the top and the derivative of the bottom, and then the limit of the left side will be equal to the limit of the result, provided the result actually has an existent limit, either a real number or infinity or minus infinity. So in this case, this says that this expression is equal to the limit, so it's the same limit as x goes to 1 of, OK, so the derivative of the top is ax to the a minus 1, and the derivative of the bottom is bx to the b minus 1. So L'Hopital's rule says that these 2 limits are equal provided that the second limit exists. So what is the second limit? Well, we can do some simplifications here. Here, there wasn't a lot of obvious simplifying to be done, but here there's an obvious simplification step. So this is equal to the limit as x goes to 1. So a over b is just a constant. And now the powers of x, this is x to the a minus b. But as x goes to 1, x to the a minus b goes to 1, no matter what a and b are. So at this point, this isn't an indeterminate form anymore. This is a nice simple limit we can just plug in. So this is just equal to a over b. OK, so that's part A, straightforward application of L'Hopital's rule. Let's go look at part B. So part B asks us for the limit as x goes to 0 of sine 5x over x. So I'll put that right here. Maybe I'll draw a little border. So the limit as x goes to 0 of sine of 5x divided by x. So again, there's a question of, is this limit, do we know what it is already? And the answer is maybe we do and maybe we don't, but suppose we don't. So in that case, can we apply L'Hopital's rule? Well, we check, and as x goes to 0, sine of 5x, so as x goes to 0, 5x goes to 0, so sine of 5x goes to 0, and x goes to 0, so this is another 0 over 0 form, so we can apply L'Hopital's rule. So L'Hopital's rule says that this is equal to the limit as x goes to 0 of, well, we take the derivative of the top and divide by the derivative of the bottom. So the derivative of the top is just 5 cosine 5x, and the derivative of the bottom is 1. So L'Hopital's rule says the limit here is equal to the limit here, provided this limit exists. And now, as x goes to 0, well, OK, 1 is constant. So we're just looking at the limit of cosine 5x here. As x goes to 0, that just approaches 5 times cosine of 0, which is 1. So this is equal to, sorry, the cosine of 0 part is 1. So it's 5 times 1, which is 5. Now I should note that that we didn't actually really need L'Hopital's rule for this one. One thing you can remember is that this limit is actually the definition of the derivative of sine of 5x at x equals 0. So what we just did with L'Hopital's rule was use the derivative to compute the derivative, if you like. So we used the fact that we already knew the derivative in order to compute it. We could also just say, by definition, this is the derivative of sine 5x at 0, which is 5 cosine of 0, which is 5, rather. OK, so that's part B. Now, part C asks for the limit as x goes to 0 of x squared minus 6x plus 2. Did I do that right? Yes. Over x plus 1. So this limit, you can't apply L'Hopital's rule. Why can't you apply L'Hopital's rule? Well, because it's not an indeterminate form. This limit is really easy to compute. You can just plug in x equals 0 here. The top is going to 2, and the bottom is going to 1. So the whole limit is going to 2 divided by 1, which is 2. So there's no, you don't need L'Hopital's rule, and also you can't apply L'Hopital's rule. This is not a form in which L'Hopital's rule applies. It's not an indeterminate form. OK, so, but the result is very easy to compute. Good, so that's 2, and we've got our last one now, which is D, the limit as x goes to infinity of ln of 1 plus e to the 3x quantity divided by 2x plus 5. OK, well, is it obvious what this limit is? Not to me. So then we can check. Can we apply? It's a quotient. So can we apply L'Hopital's rule? Well, we can apply L'Hopital's rule if it's an indeterminate quotient. So what's happening is x goes to infinity. Well, let's do the bottom first because that's easy. As x goes to infinity, 2x plus 5 goes to infinity. And OK, as x goes to infinity, e to the 3x goes to infinity. So 1 plus e to the 3x goes to infinity. So log of 1 plus e to the 3x goes to infinity. So this is an infinity over infinity form. That's an indeterminate form, an indeterminate quotient. So we can apply L'Hopital's rule. So L'Hopital's rule says that this is equal to the limit of the quotient of the ratio of the derivatives, provided that limit exists. So this is equal to the limit as x goes to infinity of, OK, so we need to look at the ratio of the derivatives. So the bottom one is easy. That's 2. For the top one, to compute this derivative, we need to use the chain rule here. So you take the derivative of this, and you get, well, it's a log. So in the bottom, we get 1 plus e to the 3x. And then by the chain rule, up top, you get 3 e to the 3x. Or just rewriting this a little bit in a nicer form, this is the limit as x goes to infinity of 3 over 2 times e to the 3x over 1 plus e to the 3x. All right, so now the question is, what do we do from here? Well, is this limit obvious? Well, OK, so there are two situations here. One is you might look at this and you might already know what this limit is. And the reason you might know that is that x goes to infinity, e to the 3x is going to infinity, and e to the 3x and 1 plus e to the 3x is going to infinity. So this is an infinity over infinity indeterminate form. And so you could apply L'Hopital's rule to it again. OK, that's one thing you could do. But you might also look at it and say, well, these two things are going to infinity at exactly the same rate. Right? This plus 1 is almost totally irrelevant. I mean, actually, for purposes of estimating the magnitude of this fraction, it is totally irrelevant. When you take, when 3x is big, then say e to the 3x is like a billion or something. So e to the 3x is a billion, so you have a billion over a billion and 1. Right? So it's very, very, very close to 1. And it's going to get closer and closer to 1. So, OK, so if you didn't trust that analysis based on magnitudes, I mean, the idea here is just that the most significant term in the top is the e to the 3x. The most significant term in the bottom is e to the 3x. They dominate everything else that appears, which is just this little 1. So that's going to give you a ratio of 1. If you don't trust that analysis, you can apply L'Hopital's rule again. And L'Hopital's rule will tell you exactly the equivalent thing. When you take a derivative, you'll be left with 3e to the 3x over 3e to the 3x, which is just 1. So in either case, this part goes to 1, so 3/2 times it goes right to 3/2. All right, so there you have it. 4 limits computed with L'Hopital's rule. Well, one of them computed without L'Hopital's rule. Remember, you always have to check that you actually have an indeterminate form before you apply L'Hopital's rule. And that's all I have to say about that, so I'll end there.